Okay. The question over here is, what is the density of wet air in grams per liter which have a partial pressure of water of 22.5 torr at 1 atm and 300 Kelvin? We over here are given with vapor pressure of water as 30 torr and the average molar mass of air is 29 grams per mole. Okay. So, we need to find out the density of wet air, and the partial pressure of water is 22.5 torr. Vapor pressure of water is 30 torr. So, what is the difference between the partial pressure and the vapor pressure? I just want to say that vapor pressure is the pressure exerted by the gas on its condensed phase. Okay. Vapor pressure is the pressure exerted by the gas in its condensed phase. Partial pressure is the pressure exerted by the gas on the volume. Okay, which is composed of the mixtures of the gases. Okay, so this particular question in which we need to calculate out the density of wet air, and the wet air is composed of water vapor plus dry air. Wet air is actually composed of wet air. If I talk about, it is composed of water vapor, okay, plus dry air. Dry air. Okay, fine. So there are two methods to solve this question. I'm opting an easy way to solve this question. Just have a focus over here. We actually know a relationship between pressure and density. Okay, we do have an expression which is having a relationship between pressure and density D. Okay, and that particular expression we actually have read in the chapter States of Matter. The relation is density D is equals to Pm upon RT. Density D is equals to Pm upon RT. P is the pressure, M is the molar mass, R the universal gas constant, and T is the temperature. So if I just want to calculate out the density for wet air, it will be equals to the density of water vapor plus the density for dry air. Density of dry air basically. Okay. So let me write dry air in this way, dry air. Fine. So, how I'm going to write it over here? I'll just write it as Pm for water vapor plus Pm for dry air divided by RT, because R and T, they both are same. R is the universal gas constant and the temperature have been given to us as 300 Kelvin. That's why. Substitute the values. So what is the pressure, vapor pressure? Okay, I mean to say vapor pressure of water given to us 30 torr. Convert it into ATM. Okay, so vapor pressure for water is equals to 30 torr. We also know one thing, that 1 ATM is equals to 760 torr, which basically means that 30 torr will be equals to 30 divided by 760. And now the units will be ATM. Clear? So 30 divided by 760, when you'll just calculate it out, you will get your expression, your result as 0.0394 ATM. Now if I want to calculate out the pressure for dry air, okay, if I just want to calculate out the pressure for dry air, vapor pressure for dry air, so it will be basically P of dry air is equals to the total pressure minus the vapor pressure of water. Okay, so it will be the total pressure given to us is as 1 atm minus the vapor pressure of water, which is 0.0394. When you solve this particular subtraction, what you're going to get is 0.9606 atm. Substitute the values over here, because we know the molar mass of water vapor, the molar mass of water is 18 grams per mole, and the molar mass of dry air has been given to us, which is 29 grams per mole. This is the average molar mass of the dry air basically. Okay, substituted over here. So density for wet air will be equal to P pressure, vapor pressure of water, which is 0.0394 multiplied by the molar mass of water, which is 18 grams per mole. It is in ATM. Okay, plus vapor pressure. Okay, for the dry air, it's 0.9606 multiplied by 29 grams per mole, 29 grams per mole divided by R into T. The value of R, if I take in terms of liter atmosphere, it is going to come out as 0.0821 liter atmosphere per mole per Kelvin. Okay. Multiplied by T temperature, which is 300 Kelvin. So Kelvin cancels out with Kelvin. Mole, this cancels out with this mole. ATM cancels out with these ATM. We are left with the unit gram per liter. When you'll solve this expression out by taking the approximation, you'll get the result as 1.164 grams per liter. So you need to take the approximation. In case, you can just take 0.0394 as only 0.04. Okay, 0.9606 as 0.9. Okay, taking 0.0821 as 0.08 only, and it will become very easier for you to calculate out your result. Hence, I'll say the only answer correct for this particular question, that means the density of wet air, comes out to be 1.164 grams per liter. So if I just match our answer, the options given to is the option number A, which says it's 1.164 grams per liter, is the right answer to this question. Question over here is, calculate the pH of a solution prepared by mixing 2 ml of a strong acid solution of pH 3.0 and 3 ml of a strong base of pH 10. We need to calculate the pH of the solution that is prepared by mixing strong acid with pH 3, volume 2 ml, and strong base with pH 10 and volume 3 ml. Okay. So let's first of all calculate the number of milli equivalents for acid as well as number of milli equivalents for base. Then we'll see whether the solution is acidic or basic, and then further we'll proceed with the calculation of pH of a solution. Okay. So if I just calculate out the milli equivalent for acid, that means strong acid, HCl. For milli equivalent to calculate, I actually require the concentration of hydrogen ion. I actually require the concentration of the solution, and that is not given to me. The only thing given to me for strong acid as well as for strong base is the volume and the pH. So from pH, we are going to calculate out the concentration of hydrogen ion basically. Okay, so for strong acid, I'm first of all going to talk about strong acid. Okay, so for strong acid, pH, the value of pH is equals to 3, and pH is actually equals to negative log of hydrogen ion concentration, negative log to the base 10 of hydrogen ion concentration, which straight away means that hydrogen ion concentration for strong acid comes out to be 10 raised to power minus 3. Okay. Now this is the hydrogen ion concentration, the concentration value, or you can say this is my molarity, okay, for strong acid. So it's 10 raised to power minus 3 molar, basically you can say. Calculating out the milli equivalents for strong acid. So number of milli equivalents for strong acid is actually equals to the volume V in ml basically. So it will be, the volume given to us is 2 ml. Okay, so it's 2 ml multiplied by 10 raised to power minus 3. 10 raised to power minus 3 molar. So it is actually 2 into 10 raised to power minus 3 milli equivalent for strong acid. Okay, basically This we have calculated out. Okay. Talking about now the case for strong base. For strong base, the value of pH have been given to us as 10. For strong base, the value of pH has been given to us as 10. But for strong base, we need to calculate out the hydroxide ion concentration. One thing we know that pH plus POH is equals to 14. The sum of pH plus POH is equals to 14, which means the value for POH will be equals to 4. Will be equals to 4. So if I calculate out the hydroxide ion concentration, and since we know that POH is equals to negative log to the base 10 of hydroxide ion concentration. So the value of hydroxide ion will become equals to 10 raised to power minus 4 molar. Okay. Now if I want to calculate out the milli equivalents, number of milli equivalents for strong base, it will be equals to the volume in ml, which is 3 ml. Okay, 3 ml multiplied by the hydroxide ion concentration, which is 10 raised to power minus 4, 10 raised to power minus 4 molar. So it becomes 3 into 10 raised to power minus 4 milli equivalents for strong base. Now the milli equivalent for strong acid is more than the milli equivalent we calculated out for strong base, which means the solution is acidic in nature. The milli equivalents we calculated out for strong acid is more in comparison to the milli equivalents we calculated for strong base, which means the solution is acidic in nature. Okay, solution is acidic in nature. Solution is acidic in nature. And if that is so, obviously we'll be calculating out the hydrogen ion concentration. So it will be equals to the milli equivalents of strong acid minus milli equivalents of strong base divided by total volume. In a way, you can say, because how we calculate out milli equivalents? M1 V1. This is the formula for milli equivalents. M into V, volume should be in ml, and the molarity, that means multiplied with the concentration term. So M1 V1. Let the milli equivalent for strong acid be M1 V1. Okay. So M, and for strong base be represented as M2 V2, because M is the molarity and V is the volume in ml. That is okay. So M1 V1 minus M2 V2 divided by V1 plus V2. This is the expression to calculate out hydrogen ion concentration. Basically, you can also say that the hydrogen ion concentration, it will be equals to number of milli equivalents of strong acid minus number of milli equivalents of strong base divided by total volume. So it will be equals to 2 into 10 raised to power minus 3 minus 3 into 10 raised to power minus 4 divided by 2 plus 3. So when you sort this particular expression, when you calculate out this particular expression, your result will be basically 3.4 into 10 raised to power minus 4 molar. So this is actually hydrogen ion concentration. So when it's a very simple expression to solve out, just solve it, okay, and you will get the result as 3.4 into 10 raised to power minus 4 molar. This is basically the hydrogen ion concentration. But we need to calculate out the pH value also. Okay, so let's calculate out the pH value. Now pH is equals to negative log of hydrogen ion concentration, which basically means negative log of 3.4 into 10 raised to power minus 4. So it becomes negative log of 3.4 plus 4. Okay. Now the value of log 4 is actually equals to 0.60. So the value of log 3.4 will be lesser than 0.60. Okay. But more than 0.5 basically. So the answer for this particular value of log comes out to be minus 0.53. The value of log 3.4 is 0.53. So it becomes minus 0.53 since negative sign was there. plus 4. When you'll solve this out, you will get your answer as 3.47. So the value of pH of the solution, pH of a solution prepared by mixing 2 ml of a strong acid solution of pH 3 and 3 ml of a strong base of pH 10 comes out to be 4.3 comes out to be 3.47, comes out to be 3.47. So we can mark it as 3.5 if our answer is coming out as 3.47 for the pH of the solution. So we can actually mark option number B as the right answer to this particular question. Question over here is, which of the following statements is incorrect? Okay. So let's find out that which particular statement is incorrect. Talking about statement number A, in general, metallic character increases down the group and decreases across a period. Metallic character increases down the group, yes, and decreases across the period. Of course, when we move from left to right in a periodic table, when we are moving across a period, non-metallic character increases and metallic character decreases. Okay. And when we are moving down the group, metallic character, it increases. Okay, fine. It's the simple reason over here that if I talk about metals, they have tendency to lose electrons. Whereas if I talk about non-metals, they have tendency to gain electrons in order to acquire stable noble gas configuration. Okay. So metallic character, since it is increasing down the group, why? Because the number of shells are increasing and tendency to lose electrons, it becomes easier basically. Metals can easily lose electrons then. Whereas if I talk about when we are moving across a period, non-metallic character increases and metallic character decreases because now electronegativity across the period is increasing and tendency to gain electrons increasing, not to lose electrons, which means non-metallic character is increasing across a period. Okay, so statement number A, I will say it's the correct statement. It is a correct statement. If I talk about statement number B, in general, reducing property decreases down the group and increases across a period. Now, first of all, before I just tell you whether this particular statement is correct or not correct, I want to actually talk about what do you mean by reducing property. Reducing property or reducing character means tendency to lose electrons. Tendency to lose electrons. Tendency to lose electrons refers to the reducing character or a property of a particular element. In general, reducing property, it increases down the group. It should be increases down the group. It should be increases down the group and decreases across a period. Why so? We over here will talk in terms of ionization energy. Ionization energy decreases when we are moving down the group because number of shells increases. And to remove an electron from an isolated gaseous atom, it becomes easier when we are moving down the group. So tendency to lose electron, it increases down the group and tendency to lose electron decreases across a period. That means reducing property will increase down the group and it will decrease across a period. The opposite of it has been said in statement number B. So I'll say this particular statement is incorrect statement. And the question 2 is asking us about the incorrect statement only. I'll mark option number B as the right answer to this question, but we'll go for third and fourth options also. Talking about option number C, the statement number C over here. In general, the oxide formed by the element, in general, the oxide formed by the element on extreme right of the periodic table is most acidic. Absolutely right. Non-metallic oxides are acidic in nature. This you have learned in your class 10th basically. Okay, so to extreme right of the periodic table, non-metals are there. So they are highly acidic in nature. Their oxides are highly acidic in nature. So in general, the oxide formed by the element on extreme right of the periodic table is most acidic. The correct statement. If I talk about statement number D, chemical reactivity of non-metals in terms of oxidizing power increases from nitrogen to fluorine across the period. Before I tell you whether the statement is right or wrong, let me tell you what do you mean by oxidizing power or oxidizing character. So, oxidizing power means tendency to gain electrons. Tendency to gain electrons. Tendency to gain electrons. And yeah, chemical reactivity of nonmetals, if we talk in terms of tendency to gain electrons, it increases from nitrogen to fluorine across a period. Fluorine is the highly electronegative element of the periodic table. And if it is highly electronegative, the tendency to gain electron for fluorine will be actually higher. Hence, the chemical reactivity of nonmetals in terms of oxidizing power, it increases from nitrogen to fluorine across the period. The correct statement. The correct statement. The only option which is incorrect and the right answer for this particular question asked to us is option number B here. Question over here is, find the degree of unsaturation for the following compounds A, B, and C. See, over here the compounds are given to me, and if I talk about the degree of unsaturation, it is actually basically equals to the sum of number of pi bonds, sum of number of pi bonds plus number of rings present in the given compound to us. Over here, if I talk about option number A, we do not have any pi bond or the ring present. So degree of unsaturation for option number A is 0. If I talk about option number B, over here we do have pi bonds, double bond. How many pi bonds? One pi bond, two, three, and four. So basically, it will be having 4 degree of freedom. Not degree of freedom, degree of unsaturation. Okay. So option number B do have 4 degree of unsaturation. Okay. And if I talk about option number A, it is having 0 degree of unsaturation. Okay. Talking about option number C, talking about the degree of unsaturation, I'll say it's having one pi bond, the other pi bond, and the next pi bond. So it is basically having 3 degree of unsaturation. Degree of unsaturation for option number C is equals to 3. So find the degree of unsaturation for the following compounds A, B, and C. It's 0, 4, and 3. 0, 4, and 3. Option number B is the right answer to this question. Question over here is maximum enolisation takes place in. See, over here we are given with the carbonyl groups. Option number A is CH3, C double bond O, CH3, CH3, C double bond O, and CH3. Option number B is CH3, C double bond O, CH2, and CHO. Option number C is CH3, C double bond O, CH2, C double bond O, and CH3. And talking about option number D, it's in front of you. See, if I talk about the maximum enolisation takes place in which of the following case, I'll say that for this particular question, aromaticity is the key factor, key deciding factor. Aromaticity is the key deciding factor for the maximum ionization for the following compounds given to us. Why so? See, aromatic compounds are more stable in comparison to any other saturated or unsaturated aliphatic compounds. In option number D, this is the carbonyl carbon, and to this carbonyl carbon, we are having alpha hydrogen atoms present at alpha carbon, which is sp3 hybridized. So over here, enolization is going to take place, which will lead to the formation of phenol, and that is aromatic in nature. And aromatic compounds are more stable than any other saturated or unsaturated compounds. Unsaturated, saturated, aliphatic compounds I'm talking about. The rest of the all compounds, yeah, they are going to show ketoenol tautomerism, no issues in that. But the level of the extent of enolization shown by aromatic compound is higher Hence, option number D is the right answer to this question. Option number A, option number B, option number C, they are going to show enolization. Keto-enol tautomerism is going to take place in A, B, and C. But if I want to discuss for the maximum enolization part, I'll go for the aromatic compound because aromatic compounds are more stable than any other saturated or unsaturated aliphatic compounds. Okay, so we'll mark option number D as the right answer to this question.